in the industry, we have typically the problem of looking at several subsystems that can be processes that have to interact one with the other. And at the same time as you would like to have a system that is well integrated, so that takes into account all the synergies that can be developed in the system, at the same time you would like to minimize the number of interconnections between the subsystems. So now it's not a question of saying this is forbidden, but it's a question of saying I would like to have the minimum number of interactions while profiting from all the ones that have to be in place in order to minimize the cost of the system. Okay, and for doing this, we have developed an approach which is going to look at how subsystems have to interact. And in order to do this, what we are going to realize is that instead of looking at individual streams, what we are going to do is that we are going to pack the streams of the subsystems. So it means that instead of saying, okay, I have the stream A, B, and C of subsystem A that can exchange, what I'm going to say is that, okay, I'm going to look at the composite curve of subsystem A. And this will become a stream for the large-scale integration. Okay? Which will allow me then to make a heat load distribution not across between streams, but between subsystems. And I would like then and what I will do is that I will try to solve a problem in which I'm going to minimize the number of connections between the subsystems. And let me just go to the example directly. So this would be the whole the combination of all the possible combinations between the different subsystems that I have, the hot and cold streams that I have in my system. So this is the complete list of the heat that can be exchanged between the different subsystems. Okay. So what sorry. What I'm going to do now is to group the subsystems, the streams into subsystems. So I have here the heat distribution system. I have process 2, process 1, process 3, and the energy conversion. Each one is represented by a composite curve. And at the end, I have the total site that is calculated and that is resulting into the balance composite curve. So now the energy balance is closed by optimizing the flows of the different utility streams which are here. Okay, so it means that now I have on the one hand the total site that is calculated, but I have also the different hot and cold streams corresponding for the different subsystems. So what I'm going to do is that I'm going to pack these streams and I'm going to calculate the heat that is exchanged between the hot and the cold streams here, the hot and the cold streams here, etc. So I'm doing heat load distribution. And of course, what can happen is that on the one hand, I have the exchange from this one to this one, which will count for 0 because it is inside the system. And then I will have an exchange from this one to this one, which will have a value of 1. Okay? And then I will say, okay, let's minimize the number of connections. So I'm going to solve the heat load distribution by minimizing the connections between the subsystems. Okay? And I'm obtaining this kind of results. Now I have the different connections. If I realize that, for example, this one is not exchanging with this one, okay, it means that I know that all the connections between the streams that are here and the streams that are here can be set to 0. Okay? The same if I have exchange between this one and this one. For example, I don't see any relationship. Okay? So I can set all the values, the integer variables that says there is a connection between this stream and this stream to 0. So by doing this, I'm in fact solving the problem by looking at the major interactions, trying to identify which are the ones that are necessary, and setting to 0 the ones that are not necessary. So by doing this, I'm reducing the size of the problem in a very drastic way. Okay? And once I have done this, then I'm going to unpack the stream. So now I have all the streams, not anymore the subsystem, but now I'm considering each individual, and I can resolve the problem, in which I have now the interactions between the subsystems that are still accounted, but in which I'm counting now the exchange inside the subsystem. Okay? And by doing this, I will be able then to calculate the heat load distribution for the process that I'm considering. And I can progress like this until I have unpacked all the subsystems, and I will calculate, therefore, the heat load distribution, which is the first step of the work of Alberto, that Alberto has shown you. Okay. I will be able then to frame the place where we have to make the heat exchanger network design. Okay, so by the mechanism is therefore the following. I'm packing the subsystems, defining what are the necessary connections by solving a first optimization problem, and then progressively depacking the different subsystems and identifying, in fact, in the set of all the possible integer variables, the one that have to be set to 0. Okay, so it's a way to reduce the size of the problem. And we have made the comparison. So this was one example from the literature. So these are the mechanisms. So we start with the minimum operating cost. We pack the systems here. We do the heat load distributions. We obtain which are the ones that are at the end not in the list. And from there, we can then go progress until we have the complete final design. Okay? And what is interesting is that we have shown that we were able to solve first the problem. And in addition to this, we have been able to solve much larger problems. So, for example, here you have 50 streams, which were not, that cannot be solved by conventional methods. So it's really to prove that by having an approach which is pragmatic and that combines a set of solving procedures, we were much more efficient than just saying yaka and formulate the whole problem. So the whole problem was solvable here, not anymore, and in this time, and not anymore here. Okay? And look at the computation time. We are still below. So with this problem, we are still going faster than the one that was here, while this one was not converging after 24 hours of calculations. Okay, so it's really proof that this approach works well. Yeah, so I think that I have already said this. So my message here is that if you are clever or smart in using the mathematical tools, then you can solve very big problems. Okay, but of course, what I have shown, on the one hand, if you want to add constraints, then you have to have a very systematic way of doing it. So, for example, the fact that some intermediate streams might be lacking, okay, is important to add from the beginning. Otherwise, you will be able to, you will not find a good solutions. Okay, and on the other hand, you can have a system that is not solving the whole problem in one row, but instead of this, you can do a sequential approach that is guiding you towards solution. Okay, and reducing the search space, because that's really what is difficult here. We have so many options that if we do not frame and reduce the number of options, then we will never find solutions. Okay? And for the last 15 minutes, then I'm going to show you that looking at only the integration of heat is perhaps not the best solution.